In this video, we will be designing a combinational logic circuit using PLA for the given input function. We will work out 2-3 examples, and here is the example 1. For the rest of the examples, the link is given in the description box. And here the function is given f1, which is nothing but a group of minterms of 3, 5 and 7. There is another function f2 where it holds the minterms 4, 5 and 7. So with these two input functions, we have to design a combinational circuit using a PLA. This is what we are going to do. So first step, we have to create a truth table. So right now, what is the input function given? We have two functions f1 and f2. What is the number of minterms here? It is 3, 5 and 7, 4, 5 and 7. So maximum it ranges between 0 to 7, which is nothing but total minterms could be 8 when the bandwidth is from 0 to 7. So if the total minterms are 8, how many number of bits we need? It should be 2 power 3, which is equal to 8. Therefore, we need 3 bits in order to represent 0 to 7. Therefore, we are choosing 3 bits as input. One is A, B and C. We are taking 3 input bits. So, right now if we are taking 3, we will have 8 possibilities of minterms starting from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So these are the 8 possible combinations for all these 3 bit of inputs. So it is done. Right now, first step, we have to map this function along with this input variables. So, let us do it for the function f1. What are the minterms given? 3, 5 and 7. It shows that some function is available for this equivalent f1 function at 3, 5 and 7. So, in rest of the minterms, we have to mark 0 and mark 1 only at 3, 5 and 7. So, we know that this position is 0, 1, 2. At 3 we have function, because at 3 we have a function, therefore let us mark it with 1. And for 4 we don't have a function, we have for 5, 0 for 6 and 1 for 7. So at 3, 5 and 7 location we are just marking 1, 3, 5 and 7. Similarly, in the same way we have to repeat the procedure for the function f2. Where do we have at 4, 5 and 7? So let us start marking 0, first location, M2, M3, we have for M4, M5, we don't have M6 and we have M7. So at 4, 5 and 7, we are representing it with 1. So this is how we have to convert this given function into a truth table. So right now step 1 is done. So the same content is being digitized for clarity. And here is a step 2. We have to plot this function into a K-map and identify the equivalent equation for f1 and f2. Let us do it one by one. First, let us identify the expression for f1 using a K-map. So how many input variables we have? We have 3 variables, which is called A, B and C. Therefore, we are making A, B, C. Therefore, a 3 variable K-map. Therefore, 0, 0, 0, 1, 1, 1 and 1, 0. And for A, it is 0 and 1. Let us try to plot these values into the K-map. So, at location 0, we have 0. At location 1, we have 0. At location 2, we have 0. At location 3, we have 1. Because we generally write 0, 1, 2, 3. And at 4, we have 0. At 5, we have 1. At 6, we have 0. At 7, we have 1. So, we have plotted all these values into the K-map. Let us try to group. We have 1, 1 and 1, 1 combination here. Therefore, we have 2 groupings. This is a maximum possible group that we could do. When we try to write expression for this grouping, which is marked in green color, there is no common term pertaining to A, Therefore, we are considering these two terms. So, first belong to B and the second variable belong to C. Therefore, this group will yield the expression BC. When we group these two ones together, that is marked with brown, there is one common term which is A. So, we can write A. When we compare these two columns, we have 0, 1 and 1, 1, which is nothing but the equivalent of BC. 0 and 1, the bit is changing, therefore we cannot consider. This bit is common to both the groups. Therefore, we are considering C. Therefore, the expression becomes AC. So, we are writing AC. So, what will be the total function F1, which is nothing but AC plus BC. Therefore, function F1 is being identified. In the same way, we have to identify the expression for the function F2. In order to do that, again we have to take all these variables and plot it into a 3-variable K-map. Because the input we have A, B, C, 3 variables. The same A, B, C, 3 variables are being converted here. So, let us first try to map 0 at the location 0, 0 at location 1, 0 at location 2, 0 at location 3, 1 at location 4, 1 at location 5, 0 at location 6 and 1 at location 7. When we try to group, first we have to find maximum possibility. There is only 3 ones, therefore we can group only 2 at a time. So, we are grouping first 2 ones and the rest of the 2 ones in this form. So, when we try to write expression for the group that has been highlighted with brown color, one common term is A. And when we compare these two terms, it is 0, 0, 0, 1, which is nothing but BC. 0, 1, it is modifying, therefore we cannot consider C. But B is as such, but B is 0, therefore we can write it as B bar. So, the equivalent expression could be AB bar. So, AB bar. Similarly, for the one in green, one equivalent term is A. So, we are retaining A because for these two terms, A is common. And similarly, for these two terms, we have to look at the top, which is 0, 1 and 1, 1 for B and C. 0 and 1 is varying, therefore we cannot consider B. Let us take C. C is as such, directly it has been logic high, therefore we can write C as such. So, AC. AC will be the expression for this group. So, when we try to write expression for F2, it is nothing but AC plus AB bar. AC plus AB bar. Hence, we have identified the expression for F1 and as well as F2. So, step 2 is over. This is the third step. We have to create a program table for the PLA. So, right now we have derived an expression which has AC plus BC for the function F1, and similarly for function F2 we have AC plus AB bar. So, now let us identify the different terms in the expression. We have AC, which is one term, and we have BC, second term. We have AC, already we have AC. So, let us drop the repeating terms. We have AB bar. So, these are the 3 different terms available in both the expression F1 and F2. Let us bring all these into the table. AC, BC and AB bar. We have got all these 3 terms into the table. These are product terms. Right now, in order to convert this into a program table, we have to list the number of inputs. We have 3 inputs. What are all those inputs? It is A, B and C. So, in this particular product term, what are all the input terms we have? We have A, we don't have B, therefore put a hyphen. We have C, therefore we are marking with 1. Similarly, in the second product term BC, what are all the terms we have? We don't have A, we have the variable B, we have the variable C. Similarly, in the third term, we have variable A, we have variable B but in its inverted form, therefore we are marking with 0 because it is B bar. We don't have the variable C, therefore we are marking with the hyphen. So, we have based on the product terms, what are all the variables available in the product term are being highlighted in the input table. Next, we have to carry over this to the output variable pertaining to the function. So what is the expression for F1? F1 is equal to AC plus BC. That is, it is consisting of product term AC and BC. So F1, it has AC, therefore mark with 1. It has another product term BC, mark with 1. Does it contain A, B bar? No, therefore mark with hyphen. So function F1 is been mapped. Similarly, we have function F2, which consists of AC plus AB bar. Okay, so same way we have to write the function for F2. Does it contain AC? Yes, the product term AC is available in the expression, so AC is done. Does it contain BC? No, mark with hyphen. Does it contain AB bar? Yes, it has AB bar, therefore mark with 1. All these functions are directly implemented, therefore we are making with true. We doesn't have any complement form, therefore we can just mention it as T. So step 3 of creating a program table is done, where we try to list it out all possible product terms. We mapped all these based on the input variables, and then equivalent output functions F1 and F2. What are all the product terms present in the function? We mapped with 1, and if it doesn't have that particular product function, we mapped with a hyphen. So this is called the PLA program table, which is nothing but the step 3. Next we have to take it and implement in a PLA itself directly. So how many variables we have? We have A, B, C. So we should have A, its complemented form, B, its complemented form, C and its complement form. So we are trying to make wires for A complement, B complement, C and C complement. Right now we have all functions A complement, B complement, C complement. So right now, in order to make A and A complement, we need an inverter. Therefore, we are using a function. So for which A will have directly and we'll have A complemented form. We have B direct function and its complemented form. And we have C, its direct function and complemented form. So right now the table is ready. What is the advantage of PLA? In PLA, both AND gate and OR gate, both are programmable. So it is evident from the figure that both AND gate and OR gates are programmable. First, let us program AND gate. So what are all the product terms? Because AND gate is required to create this product term. So what is the first product term that we have? We have AC. Okay, so we have A. Let us mark with a cross mark. And we have another term called C. So in the same wire C, we are trying to put a cross mark. Therefore, there is a connection established at A and C. Therefore, this gate will give the product term AC. What is the next product term? Next product term that we have is BC. So, let us create a connection at B and a connection at C. Therefore, this AND gate will give a product term BC. What is the third term? It is AB bar. AB bar. So we should have a connection at A. Therefore, in the same wire A, we are having a connection. And then we should have a connection at B bar. We should have a connection at B bar. Therefore, we are establishing a connection. Therefore, this AND gate will give you a product term AB bar. So right now we have terms AC, BC and AB bar. So programming your AND gate is done. So product terms are programmed. Now we need the function F1 and as well as F2. First let us do it for F1. So F1, here what is the equivalent function that we have derived? F1 is equal to AC plus BC. So AC we have, BC we have, both product terms are ready. Right now we need to OR AC and BC together using an OR gate. Therefore we have to establish a connection between AC and BC. So AC and BC, we are going to take these two variables, give it to an OR gate, that becomes a function F1. That is what we have mentioned here. We have AC and as well as BC in the function F1. So F1 programming is done. Now we have to go and program F2. So in the same way, we have AC, BC AB bar, programming F1 is done. In order to program F2, what are all the terms that we have in F2? We have AC plus AB bar, AC plus AB bar. Therefore, we have to establish a connection with AC and AB bar. We have to OR these two terms together. Therefore, we are giving it to an OR gate and deriving the function F2. Therefore, what did we do? First, we had just an expression F1 is equal to with some min terms. Similarly, F2 is equal to with a group of min terms. We converted this into truth table. Then using a K-map, we try to derive expression and then later convert it into a program table and implemented using a PLA. Hope the explanation was clear. Thank you for watching the video.